Hi students, welcome back. Today we are going to solve the partition equal subset sum problem on LeetCode. This is a slightly complex problem, so follow through carefully. Let's look at the problem statement first. The problem statement says we are given an integer array nums. We have to return true if you can partition the array into two subsets such that sum of elements in both the subsets is equal. So we have to return true if we can split the array into two parts such that sum of the elements in both the arrays are equal. We have to return false otherwise. Okay. Let's look at the examples. So if this is the given array 1, 5, 11, 5, then it can be split into two arrays 1, 5, 5 and 11, each equal to sum of 11. Okay. So the total array sum is 22. We have two subsets each of sum 11, which is why the output is true. Now, if you look at the second example, it is 1, 2, 3, 5. Okay. The sum of these elements in this array is 11. If the sum itself is 11, you can't divide it into two parts. If the sum is 11 in the sense it's odd. You can only divide it to two equal parts if it's even. This is why this array cannot be partitioned into equal sum subsets. Okay. Now let's try to solve this with an example. Okay. Okay. Let's say we take an example of a smaller array, a simpler one maybe. Let it be 3, 2, 3, 4. Okay. Let's say this is our input array. Okay. So now what should be the sum of each subsets in this array? Let's say we partition this into two parts, okay? But our requirement is both the parts should be equal. So that means we will partition it into two partitions whose sum is equal to P, okay? And that sum will be equal to total sum of the array, which is 3, 2, 3, 4 plus 3, 4, okay? Which is equal to 12, okay? Now, each partition will be of size 6. So, essentially, our problem statement derives to, instead of dividing it into two equal sum subarrays, we can just say that find one subarray which has sum equal to half the total sum of the array. Okay. So if we solve this problem, then the original problem is solved because the rest of the array will form the remaining half. Okay. And the other point we should remember is here we have to divide it into two equal parts. So like we said before in the second example, two equal parts is possible only if sum is even. So if sum is odd, we can directly return false. Only if sum is even, then we have to apply the below solution where we find a partition whose sum is equal to the half the sum of the array. Okay. So our input is 3, 2, 3, 4. And we are saying we have to find a subset whose sum is equal to 6. 6 because it is 3 plus 2 plus 3 plus 4 by 2. Okay. If we can find such a subset, then we are saying we can divide it into two equal partitions. Okay. So for simplicity, let's consider the array indices from 1. Okay. So at 0, basically, we don't have any elements. At 1, we have number 3. At 2, we have 3 and 2. At 3, we have 3, 2, 3. At 4, we have all 4, 3 to 4. Okay. Now, how do we solve this? So at each point, right? For example, if you are just at, uh, if you are at 4, okay? If you are at 4 and you have to find some 6, okay? So there are two possible ways you can find it. Assume that you know the sum at 3, okay? Okay, you know the values for index 3. That means let's say the problem is solved till index 3. Okay, now we are trying to solve for 4. So how can you write this in terms of the previous function? So what we are saying is at 4, uh, we know that the index value, the value of the element here is 4. At 4, there are two possibilities really. You can either take 4 and add it to what is there in f of 3, okay, or skip 4 and just take f of 3, okay. So when you take 4, okay, that means at f of 3, you have to find 6 minus array of index 4. So which is 2, okay. Or if you skip 4, that means you are just taking whatever is at 3 and the actual sum 6. Okay. So what we are trying to find is at every number we are trying to see if it is a value added to the partition or not, the resultant partition. If it is, if we are adding it to the partition, we have to reduce the sum by whatever the value of the variable is at that index. Okay. Now, so now if we try to write this in an equation form, it will be f of n comma s, where s is the sum, is equal to f of n minus 1 comma s minus array of n, whatever is the value at n, or f of n minus 1 comma s. This one is when you take n, and this one is when you skip n. So at every possible value, we have two branches. Okay. Now, if we try to construct a recursion tree for this, this is how it will look like. Initially, so we said our array indices start from 0. Okay. So at 0, we don't have anything. Now, if we take 3, we go to this branch. If we skip 3, we go to this branch. Okay. If we take 3, the sum here becomes 6 minus 3. If we skip 3, it becomes 3. So the next value is 2. If we take 2, skip 2, skip 2. Similarly, this is take 2, this is skip 2. Okay. Now, here the sum is 3. Now, if you take 2, the sum becomes 1. If you skip 2, the sum stays as 3. Similarly, here, if you take 2, the sum becomes 4. If you skip 2, it will stay as 6. Okay. Then the next one is the second 3 that we have. Take 3 or skip 3. So we have to take this decision at every branch. Okay. And accordingly, whenever you take, you reduce the sum value. Whenever you skip, you retain the sum value. Now here it is take 4, skip 4. Take 4, skip 4. You can't go beyond this because it is the last value in the array. Okay. And here also I didn't branch here because the sum is negative. You can't go beyond negative. If it is negative, that means it is already false. Okay. So you need not go beyond that. Similarly, when you get a 0, that means you have already got your solution, which is here. If you got a 0, that means anything, any calculation you do further, you are just going to reduce the value. It is 0, that means you already found the solution. Okay. This is true. So now on this table, let's try to construct the truth table and see how we arrive at the solution. Okay. Now let's say, let's take a different color. So 4 minus 3, we know it is false. We reached end, still we have some number. So this is also false. This is false. 4, 0. That means we found a value. This is true. Okay. Now this one is negative. So this is false. False or false. This is false. This one is 0. So this is true. This one is false because both are false. This one is also false. This one will be true because one of them is true. this is false, this is false. Okay. Here both are false, so this is false. This one will be true. This one will be true. This one is false. Here one is true, so this is true. This is true. Here true or true, so this becomes true. So our final solution is true. Okay. So this is a recursive approach. Now if you see here, there are so many overlapping sub problems as well. For example, 3 1 is repeating. Okay. 3 3 is repeating. So we can definitely cache the result and apply a dynamic programming solution. But first, let's code the recursive solution so that it becomes clear. Okay, so let's try to write code for the recursive solution first. Okay, so first case is we have to find the sum. Okay, and if it is odd, we have to return 0. Initially, sum is 0. So for each num in nums, okay, we increment the sum. Okay, now how do we find if it is even or odd? If some percentile 2 is not equal to 0, that means it is odd. If it is odd, no solution is possible. So we return false. So this is when sum is odd. Okay, that means so now in the rest of the array, sum is even. So you can just, what will be the partition sum? Partition sum would be just by 2. Okay, now we have the partition sum. Now we can call a recursive helper, okay, which takes this nums and the partition sum and our target size. Okay, so we are saying for this total array, calculate the partitions and give it to me. Okay, now let's implement this recursive function. Okay, so we have a function which takes nums, target, and an index. Initially, the index is the whole array. Now we had few cases, right? So when it is 0, sum is 0, that means we found a solution. So it is true. And sum is negative, it is false because that means that is not possible. So let's write those boundary cases first. So if target is equal to 0, that means we found the solution, return true. If target is less than 0, that means solution is not possible in that branch. Now, since we will go down to the index, the index can go negative and array can go out of bounds. So, if we are going beyond the array, then also it is false. So, if index is less than 0, then also it is false. Okay. Now, we have covered all the boundary conditions. What do we have now? We have two choices to make. We can either take this index or skip this index. So if you take this index, what you are doing is you are partitioning nums, okay, and you will go to index minus 1. So what will be the target value? Target would be target minus nums of index. Okay, you are taking this number, so you are reducing the current index value from the target. Okay, and you will recursively obviously find the solution. Now, what is the other scenario? You can skip it. If you skip it, target stays as is, but index goes to index minus 1. So finally, if either of them is true, you are true. Okay, so this is our simple recursive implementation. Let's run this and see. Partition sum. Okay. Okay, so it passed both the test cases, but since there are so many overlapping subproblems, this recursive solution might take longer time and it will time out for bigger inputs. So let's try to convert this to a dynamic programming solution. Okay, So first let's work it out in a tabular approach. So what we are saying is, okay, so let's try to find a dynamic programming solution for this. Okay, so let's say we have a dynamic programming array of size n plus 1, where n is the length of the given inputs, and partition sum plus 1. Okay, so we are taking this plus ones to address the boundary conditions. It will just make it easier instead of writing if it is equal to 0, do this. Okay, so I have, so we will have index here and sum in this direction. So indexes are 0, 1, 2, 3, and 4. So our input array is 3, 2, 3, 4. Right? So we have 4. So we have 5 rows. Okay. And similarly, our sum was 6. Okay. So our sum would be 0, 1, 2, 3, 4, 5, 6. So first, let's initialize the base cases. Okay. Now, when the sum, so what does sum 0 mean? That means you don't have to form anything. So when the sum is 0, all of them are true, which is the one of the base conditions in our recursive solution as well. Now, when the index is 0, that means when the array is empty, you can't form any sum except for 0. So, all these will be false. Okay. These are our base conditions. Now, let's try to fill the rest of the table. Now, what will be dp of 1 of 1? dp of 1 of 1 would be dp of 0 of, so what are the values here? 3, 2, 3, 4. Okay. 0 of 1 minus 3 or dp of 0 of 1. Okay. 1 minus 3 is negative. So this is false. 0 of 1. dp of 0 of 1 is false. So this would be false. Okay. Similarly, what would be the value of it? Okay. So what would be the value of it for 1 of 2? Okay. Which means, which would be dp of 0 of minus 1, which is not possible, or dp of 0 of 2, which is false. Okay. What would be the value for dp of 1 of 3? Okay. It would be dp of 1 of, what is the value at 3? Value at 1, it is 3. So it is 3 minus 3, or dp of 1 of 3. Okay. Sorry, 0 of 3. Okay. So dp of 0 of 3 is false. 0 of 0, 3 minus 3 is 0, right? 0 of 0 is 2. So this becomes true. Okay. Now, what will be the value for this? dp of 1 of 4. 1 of 4 would be 0 of 1 or 0 of 4. Both are false. So this would be false. Again, 1 of 5 would be 0 of 2 or 0 of 5, both are false. 1 of 6 would be 0 of 3 or 0 of 6, so both are false. Okay. Now what would be dp of 2 of 1? dp of 2 of 1 would be dp of 1 of, okay, 2 of 1, right? So 1 minus 2, or dp of 1 of 1. dp of 1 of 1 is false. This is not possible. So this would be false. This is array index out of bounds. What is dp of 2 of 2? 2 of 2 would be either dp of 2 of 0, sorry, 1 of 0, or dp of 1 of 2, which would be true. dp of 2 of 3 would be dp of 1 of 1 or 1 of 3, which would be true. Okay. dp of 2 of 4 would be dp of 1 of 2 or 1 of 4, which is false. and dp of 2 of 5 would be dp of 2 of 1 of 3 or 1 of 5, which would be true. dp of 2 of 6 would be dp of 1 of 4 or 1 of 6, which would be false. Similarly, here, let me continue and construct this. Okay. So if you use the same formula and construct the entire table, this is how the table would be. Now, at the end, our solution would be length of the this column. Okay. So we constructed this entire table to derive this problem column cell value. Okay. Now let's try to write this DP solution. Okay. So what so till here it would be same. From here we will change this DP solution to recursive solution to DP solution. What we said was we need a double dimensional array to hold the previous values, just like the table we created here. So we need this tabular representation. So that would be a Boolean array, and we said it should be of size length plus 1 because we took the 0 to be a corner case, okay, boundary condition. Partition sum plus 1. Okay, we initialized it. So when we initialize, by default it would be false anyway. So initially all are false. Now what we have to do is we have to set the first column here, okay, the first column to true because anything can form a sum of 0. Okay, so for int index equal to 0, index less than or equal to nums dot length, index plus plus, okay, dp of index of sum 0 or target 0 is true. Okay, rest all are anyway false. Now we will traverse this double dimensional array, okay, from index 1, okay, because index 0 we already populated, less than or equal to nums dot length less than or equal to, okay, because our dp array starts from array index 1. Okay, now we have to traverse for the sum. So target also starts from 1 because the first row is anyway false. You can't form any sum without any numbers in the array. Okay, so this is all false, which is already false. So we have to essentially only compute this part of the table. Okay, which is what we are currently trying to do, 1 to n. Okay, target equal to 1 and target less than or equal to partition sum target plus plus. What do? We have two possibilities here. You can either skip or take. Okay, Boolean take would be, okay, dp of index minus 1 of target minus what is the value of the number at the current index. It's nums of index minus 1 because our nums array goes from 0 to n minus 1, which is why it will be nums of n minus 1. Okay, this would be take. We reduced the sum by the current value at the index, or if you skip it, you don't have to reduce it, it will just be target. Okay, now once this is done, okay, dp of index of target would be take or skip, one of them. And finally, once we have everything, we just return dp of nums dot length of partition sum. Okay, and we don't have to call this recursive function. Okay, so this case is for target equal to 0. Okay, we are just setting it to true. And for this false, our Boolean array is already false. We need not do that. Okay, for take and skip, we are handling it through the previous value that we have. There is one condition that we have to consider here, which is this might go outside the array index. If it is going outside the array index, we have to take it to be false. So we have to handle that. Okay. So if is if this is greater than or equal to 0, only then you can do this. Okay. Otherwise, you have to take the you have to initialize it to false. If it goes out of the array boundary, it is false. Okay. Now let's run this and see. We can remove this recursive function. We are not calling it anymore. Okay, let's submit this. Yeah. So this works. So what we have done is we first reduced our problem of dividing it into two equal partitions of same sum to finding a partition of size of sum equal to the array sum by 2. Okay. Then we slowly from bottom up we constructed the tabular DP to reach our solution of n minus 1. So at every point, there were two possibilities for a number. It can either be part of partition or it can't be. If it is part of partition, the further sum you are looking for will reduce by whatever the value is at that number. If it is not part of the partition, then the sum won't reduce. So you either take or skip and one of the paths will give you the result. So that's what we have done here. Hope you were able to follow through this thing. So do build the recursion tree and the DP table by hand to understand this thoroughly. Thank you so much for watching. Happy coding.